Welcome to the Unit 10, Section 1 video on factoring. The numbers that are multiplied to find a product are called factors of that product. A number is divisible by its factors. You can use the factors of a number to write the number as a product. The number 12 can be factored several ways. We can write it as 1 times 12, 2 times 6, 3 times 4, 1 times 4 times 3, or 2 times 2 times 3. Now, of all of these products, there's one that is special, and that is 2 times 2 times 3. The order of the factors does not change the product, but the only example that cannot be factored further is 2 times 2 times 3. That is a prime factorization because all the factors are prime numbers. The prime numbers can be written in any order, and except for changes in the order, there's only one way to write the prime factorization of a number, and that is using two 2's and a 3. So let's write the prime factorization of 60. So the method I'm going to use first is a factor tree, and we are going to first see what is the smallest prime number that we can divide into 60. Well, since it's an even number, the smallest prime number that we can divide into it is 2. So I'm going to split this up into 2 times 30. I'm going to circle the 2 because it is a prime number, and then I'm going to move on to the 30. And let's see if we can split that up. Well, 30 is also an even number, so that means 2 will divide evenly into it, so we can break this into 15 times 2. Again, circling the prime number along the way. Next, we have 15. Let's split that up. 2 will not go into it evenly, so we go to the next prime number, 3. 3 will divide evenly into 15, and we can break that into 3 times 5, both of which are prime numbers, so we'll circle both. Once we have all of our bottom pieces of our factor tree circled, we have nothing but prime numbers left, and we have our prime factorization. So 60 is equal to 2 times 3 times 5 times 2. The second method we're going to use here is a ladder diagram. So we're going to start with 60, and again, 2 is the smallest prime number that will divide into it, so we're going to divide 2 in to give us 30, divide 2 into 30 to give us 15, divide 3 into 15 to give us 5, divide 5 into 5 to get 1. Once you're left with 1 on the bottom, all the numbers that are left on the left-hand side, the 2, 2, 3, and 5, is your prime factorization. Now you'll notice that they're in different orders for both methods, but both answers consist of 2 2's, a 3, and a 5. You may also simplify the 2 times 2 down into 2 squared and write it as 2 squared times 3 times 5. Factors that are shared by 2 or more whole numbers are called common factors. The greatest of these common factors is called the greatest common factor, or GCF for short. So the factors of 12 are 1, 2, 3, 4, 6, and 12. These are the numbers that divide evenly into 12. If we take the numbers that also divide evenly into 32 and compare the two lists, you will find that the largest number that is shared between the two is 4. When we list out the common factors, it's just 1, 2, and 4, and the largest of those is 4. So the greatest of the common factors is 4. So the greatest common factor of 2 or more integers is the product of the prime factors common to the integers. We're going to use this in our second method in the following example. So for the first method of finding the GCF of 18 and 27, let's list the factors. So we have our factors of 18 and our factors of 27, and then we can identify what the largest factor that is shared between the two is, and that is our greatest common factor, 9. You can use prime factorization as well. We take the prime factorization of 18, which is 2 times 3 times 3, and the prime factorization of 27, which is 3 times 3 times 3. Both of these prime factorizations have 2 3's in them, so we'll pull those down, multiply them together, and we get 9 as our greatest common factor. You can also find the greatest common factor of monomials that include variables. To find the GCF of monomials, write the prime factorization of each coefficient and write all powers of variables as products. Then find the product of the common factors. So in example 3, we're going to find the greatest common factor of each pair of monomials. So let's start with 3x to the third and 6x squared. We write the prime factorization of 3x to the third, which is 3 times x times x times x. 6x squared can be written as 2 times 3 times x times x. Both of these prime factorizations share a 3, an x, and another x. So we take those three pieces, multiply them together, and our prime factorization, or our greatest common factor rather, is 3 times x, which is 3x squared. For the next one, we have 4x squared and 5y cubed. Again, we're going to write our prime factorization of each. And when we do, we find that there is nothing shared. So therefore, the greatest common factor of 4x squared and 5y cubed is 1. When you have no pieces of the prime factorization being shared, the greatest common factor will be 1. Now that we know how to find the greatest common factor of numbers and monomials, we can learn our first factoring technique, which is factoring by using the greatest common factor. Recall that the distributive property states that AB plus AC equals A times the quantity B plus C. The distributive property allows you to factor out the GCF of the terms in a polynomial to write a factored form of the polynomial. A polynomial is in factored form when it is written as a product of monomials and polynomials that cannot be factored further. The expression 2 times the quantity 3x minus 4x is not fully factored because the terms in the parentheses have a common factor of x. So let's take a look at this example. 4x squared minus 3x. We can factor an x out that is shared between the two, but there is no common factor for the number. So we'll factor an x out of the 4x squared, which gives us x times 4x. We'll factor the x out of the 3x, which gives us x times 3. And we will finish by pulling that x out, kind of doing the opposite of the distributive property. Now we can easily check our work by using the distributive property on our answer and multiplying that x back out across the terms to see if we get back to our original problem. So x times 4x is 4x squared, x times negative 3 is negative 3x. So we get back to our original problem, so therefore we have factored it correctly. For this one, we have y as a common factor, but if you look at your numbers, there is also a number that can be divided out of each of our three coefficients, and that is 5. So I'm going to pull a 5y out of each term, and that's going to give us 5y times the quantity 2y squared plus 4y minus 1. Looking at that trinomial, there is nothing left that we can pull out, so we are factored. Now let's check it by multiplying that 5y back across the trinomial, and we get back to our original problem. So it is very easy to do a quick check to make sure that your answer is correct and still equivalent to what you began with. Sometimes the GCF of terms is a binomial. This GCF is called a common binomial factor. You factor out a common binomial factor the same way you factor out a monomial factor. So in this example, let's take a look at A here. Well, you'll notice that the first term has an x minus 3, and the second term also has an x minus 3. So we can simply factor that out, and that leaves behind the 7 minus 2x. In this one, you notice that we have an x plus 4, and the other term has a 4 plus x. But remember, it doesn't matter what order addition happens in, it's still going to be the same. 4 plus x is the same as x plus 4. So I'm going to rewrite that second binomial as x times 4, or x plus 4 rather, and then we'll factor out the x plus 4, leaving behind the 9x minus 5. You may be able to factor a polynomial by grouping. When a polynomial has 4 terms, you can make 2 groups and factor out the greatest common factor from each group. So in this first one, we have 12a cubed minus 9a squared plus 20a minus 15. So I'm going to group the first 2 terms, and I'm going to group the second 2 terms. Now I'm going to see what common factor I can pull out of the first 2 terms, and that's going to be 3a squared. That leaves behind a 4a minus 3. I would like to pull out something in the second 2 terms that is also going to leave me with a 4a minus 3. And if I factor out a 5, that will give me my 4a minus 3 left over. Now that I have 4a minus 3 as a term in both, I can factor that out, leaving behind the 3a squared plus 5. In this example, we'll group the 2 sets of terms. In the first 2 terms, I can pull out an x squared. I can also pull out a 9. So I have 9x squared times x plus 2. Now, I already have x plus 2 in the second, so I'm going to pull out a 1, because 1 times x plus 2 is the same as x plus 2 on its own. Now I can pull the x plus 2 out, and that leaves behind a 9x squared plus 1. Recognizing opposite binomials can help you factor polynomials. The binomials 5 minus x and x minus 5 are opposites. Notice 5 minus x can be written as negative 1 times x minus 5. Because if I distribute that negative 1 across, I'll have negative x plus 5, which is the same as 5 minus x. Be careful here. Addition is the same no matter what order you put things in. That is not the same for subtraction. 5 minus x is not the same as x minus 5. But we can have something that looks similar by pulling out the negative 1. So let's take a look at this. Negative 1 times x minus 5 is the same as negative 1 times x plus negative 1 times negative 5, which gives us negative x plus 5, which is 5 minus x. So 5 minus x is the same as negative 1 times the quantity x minus 5. So let's use this in this example. First, we're going to group the first 2 terms and the second 2 terms. We're going to factor out a 3x squared in the first 2 terms. We're going to factor out a 2 in the second 2 terms. Now that leaves us with an x minus 5 in the first term and a 5 minus x in the second term. Let's factor a negative 1 out of that second term so that we can change the order of that binomial. That's going to give us 3x squared times the quantity x minus 5 minus 2 times the quantity x minus 5, and we can factor our x minus 5 out to leave us with x minus 5 times 3x squared minus 2. Previously, you learned how to multiply 2 binomials using the distributive property, or the FOIL method. Now you will learn how to factor a trinomial into 2 binomials. We're going to reverse the process. Notice that when you multiply x plus 2 and x plus 5, the constant term in the trinomial is the product of the constants in the binomials. 2 times 5 gives us 10. Okay, look at the constant term in that first binomial, which is 2. Constant term in the second binomial, which is 5. Multiply those 2 constant terms together, you get the constant term in the trinomial, which is 10. You can use this fact to factor a trinomial into its binomial factors. Look for 2 numbers that are factors of the constant term in the trinomial. Write 2 binomials with those numbers and then multiply to see if you are correct. So let's factor x squared plus 19x plus 60 by guess and check. Write 2 sets of parentheses. The first term is x squared, so the variable terms have a coefficient of 1. So your first term of your first binomial is x. The first term of your second binomial will be x. Now we just need to find the constant terms of our binomials. The constant term in the trinomial is 60, so we're going to try factors of 60s to see if we can find the constant terms in the binomials. So we'll start with 1 and 60, which are factors of 60. That will multiply to give us the last term, but when we multiply out the binomials, our middle term is 61x, and that is not the 19x that we're looking for. So we move on to the next set of factors, which are 2 and 30. That gives us 32x as the middle term. So that still doesn't work. 3 and 20 still does not work. That gives us 23x as the middle term. So we move on to 4 and 15, and that does give us a 19x as our middle term. So the factors of x squared plus 19x plus 60 are x plus 4 and x plus 15. And we can write it out as x squared plus 19x plus 60 equals x plus 4 times x plus 15. The guess and check method is usually not the most effective method of factoring a trinomial. Look at the product of x plus 3 and x plus 4. When we use the FOIL method, we end up with the trinomial x squared plus 7x plus 12. Notice that the coefficient of the middle term is the sum of 3 and 4, because your outer gives you 4x and your inner gives you 3x. And you add 4x and 3x together, those are your like terms, to get your 7x. So the third term is the product of those same numbers, 3 and 4. So we can use this fact to have a more precise way of factoring trinomials with a leading coefficient a equals 1. To factor a quadratic trinomial of the form x squared plus bx plus c, find two factors of c whose sum is b. If no such integers exist, the trinomial is not factorable. When c is positive, its factors have the same sign. The sign of b tells you whether the factors are positive or negative. When b is positive, the factors are positive, and when b is negative, the factors are negative. Remember, this is only the case when c, your constant term on the end, is positive. So let's check out a couple of examples. Let's start with x squared plus 6x plus 8. We are going to find the factors of 8 that add to give us 6. So we start off with 1 and 8. Those add to give us 9, so that's not going to work. 2 and 4 multiply to give us 8 and add to give us 6, so that does work. So therefore, we can factor that trinomial into x plus 2 times x plus 4. Now, of course, you can check this by multiplying those two binomials back together, using the FOIL method and simplifying, and that does return us to our original problem. So this is a factor form of your trinomial. In B here, we have two numbers that are going to multiply to give us 16 and add to give us negative 10. We know both numbers have to be negative because we are multiplying to a positive, but we're adding to a negative number. So we start with negative 1 and negative 16. That's going to give us negative 17. That does not work. Negative 2 and negative 8 give us negative 10, and that does work. So we can factor it into x minus 2 times x minus 8. And we can again check this by multiplying the binomials together to see if we return to our original trinomial. When c is negative, its factors have opposite signs. The sign of b tells you which factor is positive and which is negative. The greater factor has the same sign as b. So in this first example, you notice that we have to multiply to negative 18. So therefore, one of our factors has to be positive, the other has to be negative, because a positive times a negative will give you a negative. But our middle term is positive, so that means the greater of the two factors has to be positive, since we have to add those two factors to a positive number. So we'll start off with negative 1 and positive 18, and that's going to give us a sum of 17. That is not going to work for us because that's not our middle coefficient. So we move on to negative 2 and 9. Negative 2 plus 9 gives us 7. That is our middle coefficient, so we can factor it into x minus 2 times x plus 9. For the next one, we have x squared minus 5x minus 24. Since our last term is negative, we're going to have a negative and a positive. And since the middle term is negative, the larger number has to be negative. So we're going to look at the factors of negative 24. 1 and negative 24 add to give us negative 23. That will not work. 2 and negative 12 give us negative 10. That will not work. 3 and negative 8 give us negative 5, and that is our middle coefficient. So we can factor this into x plus 3 times x minus 8. Now you will factor trinomials of the form ax squared plus bx plus c, where a is greater than 1. Recall the FOIL method for multiplying binomials such as 5x plus 2 and 3x plus 7. We can multiply it out doing first, outer, inner, and last. That's going to give us our two middle terms of 35x plus 6x, which we can then combine to get our final trinomial of 15x squared plus 41x plus 14. Now, the binomials 5x plus 2 and 3x plus 7 are factors of 15x squared plus 41x plus 14. Notice that 15 times 14, our leading coefficient, and our constant term on the end multiply to give us 210. Look at the two middle terms before we combine them. We have 35 and 6 as our coefficients. When you multiply 35 and 6, you also get 210. And remember, a lot of math is looking for patterns and seeing how we can use those patterns. We can use this information to reverse the process to factor trinomials such as 2y squared plus 7y plus 6. The product of 2 and 6 is 12, our leading coefficient and our constant term on the end. We need two integers whose product is going to be 12 and whose sum is going to be 7, because that product of the first coefficient and the constant term is going to be the same as the product of the two middle terms before they are combined. So let's use guess and check to find these numbers. Factors of 12 that are going to add to give us what we need. And when we go through those factors, we need the sum of 7, and 3 and 4 are the factors of 12 that will add to give us that 7. So we are going to take that middle term of 7 and we're going to split it into 3 plus 4. That gives us our two middle terms of 3y plus 4y. Now we can group the first two terms and the second two terms, so we can factor by grouping. And that's going to give us 2y plus 3 times y plus 2. This method for factoring ax squared plus bx plus c is called the AC method because you multiply a and c to find the number that you need factors of. So let's do an example. We need factors of 70 because 5 times 14 is equal to 70 that are going to add to give us negative 17. So we have negative 1 and negative 70, which is negative 71. That will not work. Negative 2 and negative 35 will not add to negative 17. Neither will negative 5 and negative 14, but negative 7 and negative 10 will. So we're going to split up that middle term into negative 10 and negative 7, which gives us our two middle terms. Then we group our first two terms and our second two terms. And then we do our factoring of each set of terms to give us our final factored form, 5x minus 7 times x minus 2. Previously, you learned that the difference of two squares has the form a squared minus b squared. The difference of two squares can be written as the product a plus b times a minus b. You can use this pattern to factor some polynomials. A polynomial is a difference of squares if there are two terms, one subtracted from the other. Both terms are perfect squares, such as 4x squared minus 9. We can split up 4x squared into 2x times 2x and 9 as 3 times 3. So, difference of squares, when you have a squared minus b squared, it's going to be equal to a minus b times a plus b or a plus b times a minus b. Remember, multiplication doesn't matter which order you multiply in, you're going to get the same thing. So you can write it either way, starting with your plus and then doing your minus, or starting with your minus and doing your plus. So the factored form of what you see on the screen here would be 2x plus 3 times 2x minus 3. So let's factor a squared minus 64. We have a square, perfect square for the first term, because a squared is simply a squared. That's fairly straightforward. 64 is a perfect square. It's 8 squared. So we can factor it into a minus 8 times a plus 8. 9x squared minus 100y squared. 9x squared is 3x quantity squared. 100y squared is 10y quantity squared. So this factors into 3x minus 10y times 3x plus 10y. For 12x cubed minus 27xy squared, we first have to factor out a 3x. That's our greatest common factor between the two. Now, once we have the 3x factored out, we're left with 4x squared minus 9y squared. Both of those are perfect squares, so we can factor it into 3x times 2x minus 3y times 2x plus 3y. Numbers such as 1, 4, 9, and 16 are called perfect squares since they can be expressed as the square of an integer. Products of the form a plus b quantity squared and a minus b quantity squared are also perfect squares, and the expansions of these products are called perfect square trinomials. So a perfect square trinomial is defined as such: a plus b quantity squared is a squared plus 2ab plus b squared, and a minus b quantity squared is a squared minus 2ab plus b squared. So you notice the only difference between the two is the sign of your middle term. To determine if a trinomial is a perfect square, you must be able to answer yes to these three questions. Is the first term a perfect square? Is the last term a perfect square? Is the middle term twice the product of the square root of the first and last? If you can answer yes to all three, then you have a perfect square trinomial and can use this form to easily factor it. So let's take a look at this trinomial, x squared plus 22x plus 121. First, we need to determine if it's a perfect square trinomial. Is the first term a perfect square? Yes, it is. Is the last term a perfect square? Well, 121 is 11 squared, so yes, it is. So now, in the process of answering these two questions, we have found what the square root of the first term and the last term are, that they are x and 11 respectively. So, is the middle term twice the product of x and 11? Well, 22x is 2 times x times 11, so yes. So we can factor this down into x plus 11 quantity squared. Square root of the first term plus the square root of the last term, and we will square that binomial. Let's do another one. Let's find out, is 16a squared a perfect square? Well, it is 4a quantity squared, so yes. What about 81? Well, yes, that is 9 squared, so that is a perfect square. So is 9 times 4a times 2 going to give you 72a? And yes, it is. So we can factor this down into 4a minus 9 quantity squared. We use minus this time because the middle term has a negative sign. Let's try this one. 9p squared minus 56p plus 49. The first term is a perfect square. The last term is a perfect square as well. So if we take 7 times 3p times 2, do we get 56p? And the answer to that is no. So since that third requirement does not work out, we do not have a perfect square trinomial, and we may have to look for another method to try to factor this, if it is factorable at all. Thanks for checking out my video in the Algebra 1 Honor Series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.